Well, first I want to thank the speakers we had this morning because I wasn't sure what to talk to you about, and then I basically followed what they were doing. Agda started in 1999 in Gothenburg. It was designed by Katarina Coquan, and that was the Agda 1 system. And then for his thesis in 2007, Ulf re-implemented the system from scratch and described a lot of useful features I will show you later on. It's developed openly on GitHub as Rock is and as other systems are, but the core developers are mainly based in Sweden and Belgium. It's always nice to go visit and work with them on possible extensions. And talking about meeting, we have 2 week-long meetings every year to work on the system or in the system. So it's not just for the core developers. If you're an active user, you want to get some help from experts to work on your formalization, you're very much welcome to join the meeting and spend a whole week. All right, so contrary to popular belief, we don't just type check our programs, and it's not just a theorem prover. So even though this is a school on formalizing mathematics, I thought I would start with the fact that it's a programming language. So it's a dependent type programming language. I will explain maybe a bit more about that later on. But importantly, it has pluggable backends. The main ones are based on Haskell, but in theory, you could just define your backend of choice. Some of them, so the default one targets almost all of the language. There are issues with like bleeding edge features that are not translated. And then there are more restricted ones. For instance, there's an Agda to Haskell backend that is trying to generate readable Haskell. And that means that you cannot use all of the features of Agda because not all of them can be translated into Haskell. We have a powerful FFI, so you can use anything from the Haskell ecosystem. You just have to write the bindings. This is the categorical just. There's actually a lot of work involved in writing bindings, but if you have time, you can do it. And of course, there are escape hatches because you may want to prove theorems and then you want to be really sure that the proof is correct and everything is true. So we have a strong termination checker, positivity checker, and so on. But sometimes when you're programming, you don't really care about being as systematic about your proofs. So you can just say, okay, trust me, this is positive or this is terminating. But of course, Agda is also a theorem prover. And so unlike Rock, it's not based on type theory, it's based on type theories because it's more of a playground for PL researchers. They can, if you provide an implementation that doesn't break too many things, if it breaks a lot of things, then maybe it's hidden behind a pragma or something, behind an option that's not turned on by default. But in theory, you could extend the system with whatever you want, as long as it's sort of compatible. So the core is Martin-Löf type theory, but then we have lots of extensions, talking about 2-level type theory, which is this language that allows you to do a lot of meta mathematical reasoning directly in the system to generate at the higher level theories in the core level. Then we have, so I don't know if you're familiar with Axiom K, but you can turn it on or off depending on what you want. There's cubical Agda, famously, there's strict prop, size types, which are widely inconsistent at the moment. And we used to have TT in color, and then which is a way to internalize parametricity. I don't know if it's something a statement you recognize, but and then it was pulled out of the system because there were no maintainers for it. But basically, the message is that if you have a really cool type theory that is mostly compatible with core MLTT, as long as you're willing to be the maintainer for that thing, you might be able to add it correctly. So yeah, as I said, it's foundations a la carte. Through options, you can just turn things on and off. Oh, I removed the warning. Okay, there was a warning saying that things, some extensions are incompatible, of course, if you turn both of them on at the same time. well, it's your problem, you shouldn't have done it. But there's a more conservative, safe option, which will actually reject turning these incompatible options on at the same time. So if you want to prove theorems, then you should probably have a safe on by default, which means that then there's a lot of things you cannot do. So you cannot add compilation pragmas and so on, because these are typically explaining how to translate Agda definitions into Haskell ones, and there's no way to check that the translation you're specifying is actually correct. So you're giving up a lot of power, but then if you're trying to publish your paper, you can say, okay, let's check by safe. So it probably is fine. There are, of course, some soundness bugs. Yeah, there we go. So at the moment, there's 11 of them open, 60 are closed. So I mean, we've done some good work. But out of the 11, I checked, and I think only one is in the safe part of the language. So that's really bad. I mean, it's a software project. So.
What is the false tag?
So false is a proof of void, basically. So it's a label on GitHub to mark all of the inconsistencies, basically, so that we can quickly find them and look at them in despair. Okay, so do we have a small kernel like a lot of other languages? Well, no. That's not completely true. So Jesper got a lot of funding from the Dutch government, so you actually try to, or is it the Belgian one? I can't remember. To work on these problems. Turns out it's really hard because, as I said, we have foundations a la carte. So if you want a core language, you first need to decide what it is. And then, as I'm going to explain a little bit later, Agda has a lot of really powerful mechanisms that are really hard to specify and to prove correct. The language, turns out, is actually quite big. So the implementation is the specification at the moment, which is a bit unsatisfactory. So yeah, Jesper recently published a blog post explaining the challenges of building Agda core, and he has an online repository where parts of Agda is, of this idealized Agda core is written in Agda itself. Do we have automation? Well, no. Well, that's not completely true. So Agda has an extremely powerful elaboration machinery, and the programming style that you tend to adopt when you're working in Agda actually removes a lot of the work. So dependent pattern matching is an extremely powerful tool that is not as used in other languages. Unification allows us to reconstruct arguments that are not specified by the user, and it does so in a principled manner. I haven't written it for some reason. We only generate unique solutions. In Coq, sometimes there's a bit of like magic, and we're picking a solution that's not unique, hoping it will work. Here, all the solutions picked by the machinery are unique, and so you know that if there's a statement, there's only one possible meaning for it. We have parameterized modules, which is also something that's really powerful, although fairly simple, I guess. We have a meta-programming mechanism, so this notions of type tactics. It's underused, so there's an avenue for research here. Part of the problem is that then you're relying on the evaluator for the language to run these tactics inside the language itself, so it can become a bit slow if you're not careful about the way you implement them. And you have to do a lot of work by hand, which is already done in the compiler, which is a bit annoying, this kind of situation. And we have a form of dependent type providers, which means that at compilation time, you're able to make an I/O computation and grab some information from the outside world to generate a type or proof or whatever you want. But again, this is not extremely developed in the community. The tools, the primitives are there in the language, we just haven't used them a lot. So if you're thinking of contributing to Agda this week, I've put you a list of different projects that give you kind of the flavors of the Agda project. So we have the standard library. For a very, very long time, installing packages was really hard, almost impossible. Nowadays, it's just really hard. So a lot of stuff went in the standard library instead of having everyone have their own small libraries. There's a category theory library developed by Jacques Carrette. I don't know if it's here. He's one of the organizers of the.
Not yet.
Coming in June.
Okay. So you can talk to him. It's a new kind, a new view of category theory because it's embracing setoid. I don't know if you're aware of the setoid issue, but it's just going all in with it and trying to reformulate usual results in terms of setoid and doing it nicely. There's cubical Agda, of course, because of all the homotopy related things. There's this work on the semantics of programming languages. So there's a logical relation for MLTT. And this is probably what I'm going to try to work on this week. Try to understand how it works and maybe extend it a little bit by adding more construct to the language. There's Martin Escardo's library of homotopy-related results. And then, as I said, we have dependent type providers. So WEN is actually one of the people who use them to bind SMC solvers. Maybe I can click on this, but I don't know how much time I have.
Okay. Maybe a bit less.
Yeah. So this is the kind of, okay, I zoomed in too far. This is the kind of lemmas where you can just invoke Z3 and it will prove the theorem for you using this mechanism allowing you to hook any I/O computation during type checking. So this is a very innovative use of this feature. Right, so then this is when I go on my rant. So I don't know if you're aware, but at CMU there's this fake conference every 1st of April that's organized by students. It's called SIGBOVEC, and you can. No. Okay, well I don't think the ref accepts submissions from SIGBOVEC. But a few years back I sent this thing. So you define a type as a function from strings to bool. And then what it means for a term, a string, to be a member of that type is to run the computation and get true back. And then you can define 0 as the string z. You can define successor as the thing that just puts an s in front of an existing string that's already a natural number. And it turns out that you can actually prove the induction principle for this thing, and then you can, and it has the right computational behavior on the constructors and everything. So you could theoretically program in this manner, right? And I won't name names, but when I was a student, I attended some mathematical lectures where we started from bit strings, and then we're trying to explain which ones were well formed, and then which ones were well behaved, and so on. And this is very much the lesson from Agda is to just don't do this. Just stop doing this. Like, it's horrible. You cannot do deeply. Okay, you can use the eliminators to program, and they have the right behavior, so you will be able to prove your theorems and so on. But as soon as you want to do something that the eliminator is not providing, like deep pattern matching, for instance, you have to go back to the encoding, and then you have a lot of garbage in your source. So in here, the terms are all of the strings. So if I want to do a deep pattern matching, I need to start eliminating all of the garbage explicitly. And why would you do this when you can just declare the inductive type by its constructors? And Agda pushes this really far. So it pushes this idea of always using the right data for the objects of study. And so you start with inductive types for like the natural numbers, like I showed you. Then you have inductive families. If you have something that's indexed by an inductive type, and you're trying to specify a predicate over it, for instance. Then you have this notion called induction, which allows you to define mutually a type and a predicate over it, so that you can restrain the shape of the type. Then you have induction recursion, which allows you to define both a type and a function over it at the same time, and both of them can reference each other. And then, I mean, I've put it afterwards, but it should be in a separate branch, basically, because cubical brought us higher inductive types, where you can talk about the higher structure of a type, of the equalities of that type, what kind of structure they have. You can quotient a type by some extra equalities, for instance. And then, of course, we have higher inductive types. I don't know whether it's implemented or not. And you could keep pushing this way. I think I have an example. Oh, I forgot to. Right. So this is the example, right, where we're starting from inductive type. So we're defining this list with two constructors. We're not talking about list of characters, right? We're not talking about strings and then specifying which ones are proper list of A's. We just declare the list of A. And then if you want, you could define, some white space so that we don't yet see the rest. We can define what it means to have the predicate lifting of P over the list. So if the list is empty, then it's trivially true. So we also use this constructor. We just overload the constructor. Oops. And if the list is non-empty, then we require proof that P holds of the head of the list and also that it's true of all of the elements in the tail of the list. So that's what these two arguments are doing. And then an example of induction recursion, because it's not, maybe not clear what it means to declare a data type and a function over it at the same time. So this is a notion of fresh lists for this relation R that tells you when two elements are distinct from each other. And so the empty list is trivially fresh. And then if you put an element at the front of a fresh list, well, it better be a fresh one according to the elements in the list. And what does it mean to be fresh according to a list? Well, you can define it by recursion over what it means to be a list. So X is always fresh with respect to the empty list because there's nothing else in it. And then if you have a head and a tail, you just demand that X is distinct from Y and then that X is fresh in the tail of the list. So you can see that this function is both showing up in the inductive definition of list and also and the type list is showing up in the type of the function. So that's what it means to have the definition by induction recursion. And then finally, we have this thing which I claim is the sort of set. So you can construct the empty list, you can put an element at the front of the list, or maybe, and then you can quotient this new data type over new equalities that you just throw in. So you're saying, okay, swap tells you that if you have a list that starts with X and Y, it's the same as the one that starts with Y and X. So you're saying it's list modulo permutation of the elements. And then crush allows you to remove any element that is related to one that's already in the list. So here it's formulated into the ones at the start, but because you can swap things around, they're just with respect to any of the list. And I forgot to say something about...
But isn't that relation like being distinct?
No, so the relation is a parameter here.
Oh, it's another R.
So you can pick whatever you want. Yeah.
How come it's set value instead of prop value?
Because it's a
So
type.
it's actually a data type. You actually care about the content of the...
I think R is just like, could I have R KA rule if I felt like being less?
Oh, the relation. Yeah, sure. Yeah, it doesn't have to be. Yeah.
Can you show us the, you have to say Rxy equals true, which is... Can you show us the
No, it could be a problem. Yeah. Sorry.
definition of the equality?
Oh. Yeah, it's a path where the type is constant along the path.